Given y is equal to x cubed plus 2x squared minus x minus 2, if we're asked to find the y-intercept of this given function, we will start by setting x is equal to 0. We will then write the given function and replace x with 0. Solve the given function, and in this case, y is equal to negative 2. Therefore, the y-intercept is negative 2. So how can we see visually this y-intercept, which is negative 2, in our given function? If we're going to graph this in our Cartesian plane, this is how the graph looks like, represented by this given function. Notice that this graph crosses the y-axis at exactly negative 2. This negative 2 is called the y-intercept. To solve for the x-intercept, inversely, since we're looking for the x-intercept, we will set y into 0. We will then write the given function, then set or replace y with 0. And we're going to find the x-intercept. Now, we're going to use trial and error in order for us to solve this. Now, to lessen our choices, we're going to use the rational root theorem. So let's start with writing the factors of our p, which is in this case the negative 2. So the factors are positive 1, negative 1, and positive 2, negative 2. Then the factors of q, which is the numerical coefficient of our leading term, which is 1, are positive 1 and negative 1. To simplify them, so this will be our rational roots, wherein the x-intercepts can be any of them, positive 1, negative 1, positive 2, or negative 2. So we're going to test them by using the remainder theorem. So let's start with the positive 1. This will be our number indicator. We will then write the given function replacing y with p of x. Then write x cubed plus 2x squared minus x minus 2. Replace x with c, which is positive 1. Then solve. And in this case, p of 1 is equal to 0. Therefore, 1 here is one of the x-intercepts. So let us try negative 1 as our number indicator. So doing the same process. So replace x with c, which is negative 1. Solve the given function. And our p of negative 1 is also 0. Therefore, negative 1 is also one of the x-intercepts. Let us try negative 2. So doing the same process, replace x with c, which is negative 2. Solve the given functions. And again, the p of negative 2 is equal to 0. Therefore, negative 2 is also one of the intercepts. Lastly, the positive 2. Replace, then solve. Then in here, unfortunately, our remainder is not 0. It is 12. So this tells us that positive 2 is not one of the x-intercepts. So thus, the x-intercepts are positive 1, negative 1, and negative 2. So how can we visually see these x-intercepts in our graph? So going back to our Cartesian plane, so focusing on the x-axis, notice that our graph crosses the negative 2 in here, then in negative 1, and in positive 1. So this positive 1, negative 1, and negative 2 are called the x-intercepts because it crosses the x-axis. The positive 1, negative 1, and negative 2. Actually, in solving x-intercepts, we have an alternative process. That is, aside from the remainder theorem, we can also use the synthetic division. And the process is just familiar to you. So we will start by using the rational root theorem in order for us to limit our guesses. And we will be using this as our number indicator. So we're going to use positive 1 as our number indicator. Doing the synthetic division, it shows that the remainder is 0 in positive 1. In negative 1, the remainder is also 0. In positive 2, the remainder is positive 12. So it's just similar with the remainder theorem. If our number indicator is negative 2, so the remainder is 0. So again, this tells us that positive 1, negative 1, and negative 2 are the x-intercepts in this given function. So we can use a remainder theorem or synthetic division. It's up to us which of those method that works for us.